Okay, so welcome back. Let's what we have done the initial part of the discussion, that like the introductions which to give you an idea about this aircraft or the propulsion and the different aircrafts, their status and state of the art situation, and that was followed by some of the basic discussion on fluid mechanics. And just to review the thing, that is not a detailed lecture on fluid mechanics or thermodynamics. So, that just to let you know that these are the things which are going to be repeatedly used. So, you can refresh your memory or go back and look at the basic thermodynamics and fluid mechanics books to refresh those information. And then finally, we did some discussion on compressible flow, where we started with one dimensional compressible flow, and then moved to normal shock relations, where we derive normal shock relations. And obviously, when you have normal shock relations, one can always also use the normal shock from the table, but these are. And then finally, we did discussion on compressible flows and the pressure and temperature variation in the atmosphere. And with that kind of background, we are all set to move for the actually the detailed discussion on our air breathing engine. So, what we are going to look at now, we are going to look at the aerothermodynamics of the air breathing engines, and where we start with some of the performance parameters. And once we look at the performance parameters, and then go in detailed discussion of each of the individual different kind of engines that we have planned for. So, let us start with the thing that what we want to do. So, as I said, we are going to talk about the aerothermodynamic of aircraft engines or aircraft jet engines rather. Okay. Now, air, when it passes through these big airlines which are quite high, so the mass flow rate it deals with these aircraft engines or the jet engines is large mass flow rate. That is very important. Now, airflow rate is also high for a airflow rate is high for a piston propeller engine. So, piston propeller. Now, a turbine is more efficient in handling large flows than a propeller. Okay. So, there is a complex in piston propeller, there is a complex gear assembly in piston propeller engine. Now, when you have that kind of propeller at high speed, there are tip shocks or tip shock waves generated, there would be noise. Now, turbojet and turbofan can operate quite reasonably at high subsonic speeds. Turbojet can be supersonic. Piston propellers are more efficient for low speed and small aircraft. Jet engines also can do VTOL and thrust vectoring. These already we have seen some of the example while doing the introduction. turbine is very efficient machine to convert flow energy to other form of energy, that is electricity and all this. So, when the gas flow through the turbine, it turns the turbine, and the rotating motion of the turbine can be used to generate the power, and the gases expands across the turbine. Now, to have gas flow across the turbine, there must be a pressure drop. So, across turbine there must be pressure drop, delta P is there. Okay. So, hence a pressure ratio across the engine must be provided. Therefore, the first necessary step in a gas turbine cycle is the compression of the working fluid. So, just to get that, so one can see compression is the first step, and that is what happens when you look at the total sequence of process. It comes to intake, and then to compressor, then compressor to combustion chamber, then turbine, then nozzle, and then finally goes out. So, this compressor is very important, and to get this compression, compressor is used, and mostly in the gas turbine these are axial flow compressor and also used in multiple stages, because when you use the multiple stage compressor we can get desired pressure rise or high pressure rise. Now, if the compressed gases are expanded directly in the turbine and there are no losses in any of them, the power developed by the turbine would be the power absorbed by the compressor. So, in ideal situation you need one compressor and one ideal turbine, that means no loss, are coupled together, and then the combination can just turn itself. So, and you will get useful, but no useful work. Now, when the turbine develops the power, or the power developed by turbine can be increased by adding energy to the working fluid. So, and that is done, the energy is added to the fluid in combustion chamber. So, this is where the fuel burns. So, you can see first the large amount of air which is kind of drawn into the system, and then there is a compressor which does the compression process. Then when it goes to the, so this increases the pressure and also slows down the flow field or the velocity. Then it goes to combustion chamber, where due to the burning of the fuel the extra energy is added, and this added energy when it passes through the turbine where the expansion takes place, the turbine produces power and it passes through the nozzle. So, due to this added energy or the hot gases which are expanded in turbine, it produces the power, and that provide the useful output. Now, if we look at a schematic of the basic gas generator. So, that is very basic of an gas generator, which you can see you have an air coming in, then this is a unit of compressor, then this after compression this air goes to the combustion chamber where the fuel burns and extra energy which is added, and then finally it comes to turbine, and then the product pass through to get the output, and the turbine and compressor sitting on the same mechanical component like a shaft. So, this can produce electricity, it can lift weight, and if the hot gases expanded through a nozzle at high velocity can produce thrust. So, that is what it happens. Now, when you look at this basic gas generator, so you have air comes in, pass through the compressor, then the combustion takes place, hot gas goes to this turbine, then this turbine is connected with the shaft to the compressor, and this is, and if you look at the cut section here, this will give you a very nice picture of the engine. So, this component from the compressor, combustor, turbine, this is what we call it the basic gas generator. Here it pass through, and you can see in compressor very interestingly why we use this kind of typical symbol for compressor, because the area actually decreases, and these are axial stage compressor, and turbine this actually increases. So, area increases. Okay. So, one can say the heart of a gas turbine engine is the gas generator, okay, which has compressor, combustor and turbine, which are major components and very common to turbojet, turboprop, turboshaft. So, the purpose of gas generator is to supply high temperature and high pressure gas. So, that is the basic gas generator, which for which this is it. Now, when we have a basic gas generator, and you can see how this development or the proceeding added component can make things complicated and increase the or enhances the capability. Now, with this basic gas generator, so we add, so by let us say adding an inlet and a nozzle to a gas generator. So, what it gets? You get a turbojet engine. So, again if you look at, this is the basic component of the gas generator, compressor, turbine, and then now we have added an exhaust and inlet. So, this is the portion which is there. Now, previously we had, and then this is the portion which is added. Now, here immediately this schematic will give you another picture, which is also quite informative, that you have two different stages of compressor. So, that means they are not also put it in on the, now one is the low pressure compressor, where area ratio is quite drastic or area change is quite drastic, and then the high pressure compressor. After this the flow pass through the combustor, then obviously when these are there, you have high pressure turbine and low pressure turbine. And one important thing is that high pressure turbine is connected with high pressure compressor, and low pressure turbine is connected with low pressure compressor. And you can see from that picture who is sitting on which mechanical component like the shaft, because the power produced by HPT partly goes to run the HPC, power produced by LPT partly goes to run LPC. These are very, very important and very fundamental information for any gas turbine engine or the jet engine. Now, here the high speed exhaust gases leaving the engine causes a net change in the momentum, which is manifested by a force generated by the engine, and this force is called thrust. Okay. So, we have seen lot of turbojet example. One of the quick just to GE J79 is a turbojet engine with afterburner or AB. That means, after turbine before pass through the nozzle, there would be secondary fuel inlet where the burning takes place. So, from the basic gas generator, when you add this inlet section and the nozzle section, we get the turbojet engine. Now, with this turbojet engine, if we add some fan now and some component, now except this fan, if you look at the rest of the portion was there in this turbojet engine. Now, when we add that component of the fan, this makes a turbofan engine. So, apart from the compressor, you have added fan sitting there. So, there are some advantages using this kind of system, but let us look at this schematic here. So, you see the fan is sitting there, you have already the inlet, then from fan, after fan the air gets splitted in two component. One goes through this bypass, this is called the bypass nozzle or the bypass section, one pass through this core of the engine. So, the one which pass through the core of the engine, that pass through the rest of the component of the gas generator, which is compressor, low pressure, high pressure, combustor, HPT, low LPT and the nozzle and the rest. So, this bypass nozzle also, so the total thrust here, the total thrust has two components, one is the thrust due to cold or the bypass and the thrust due to hot. So, you have two components which also, that means this bypass contributes to the thrust generation or the production, and what it allows that much compared to turbojet, much more air can be moved, efficiency is higher than turbojets, and it can go from subsonic to supersonic application. So, there are, that means the flow component will have that pass through the fan, then splitting. Some of these example we have seen in a detailed introduction. There are different kind of turbofan engines are application today, not only in the civilian applications, they are both in military application also, and that is the increase of turbofan engineering is more and more because of this. For example, like one can say Pratt and Whitney, JT9D, PW 4000, F100 with AB. This is used in F-15 Eagle, then G CF6, G90, F110 with AB, which is also used in F-16 Falcon. Then you have Rolls-Royce, which is RB211, 524G, H. You have Snecma, CFM 56. So, these are some of the examples, but the exhaustive list is already kind of discussed during introduction. Now, so that is how things gets more and more. Once you add one after another component, things get more complicated. Now, another is the turboprop, where we added an propeller there and ahead of the compressor. So, just to have this propeller or to run this propeller, one has to have the gearbox, which is necessary. Why? To maintain optimum speed for both propeller and core of the engine. Okay. So, you have a gearbox sitting here. Now, the schematic, if you see, there is a gearbox sitting there, and this is the section which is propeller, and this is the basic gas generator portion, which has compressor, LPC, HPC, combustor, HPT, low PT, and then pass through the nozzle and all this. But this is this propeller kind of configuration. Obviously, there are certain advantages and certain disadvantages. One of the big advantage with this configuration is that it can handle huge mass of air at low speed. That is one of the advantage. So, at the low speed application, this is more efficient compared to turbofan, but as I said, this is limited to low speed application, because when you go to high speed, there would be possibility of propeller tip, shock waves at high speed. So, that restricts the application at high speed, and also another advantage for the propeller engine, because of this gearbox and the huge propeller, the engine become bit bulky and heavier. So, but obviously nothing is kind of perfect. So, whenever we use something, it will come with some added advantage and come with some added disadvantage. So, these are the basic gas generator with some component like turbojet, turboprop or turbofan engines. Now, we can look at the calculation of thrust. Now, let us take a system like this, where the inlet area is AI, and this is the structural support just to keep this, and this is a free body diagram, and this control volume that we have taken, this is the inlet mass flow rate, and we have inlet, exit, station 1, 2, and then upstream velocity, temperature. So, and this is the reaction force. So, we can say that let us say steady flight in x direction, okay, and T is the reaction to the thrust transmitted through the structural support, okay. And what would be engine thrust? Engine thrust is the summation of all forces on the internal and external surfaces of the engine and nacelle, okay. Now, what we can write, let us say the momentum conservation equation for steady flow. So, this is our control volume plus control surface rho u dot n dA summation of f. So, this goes to 0 because steady assumption. Now, what we can do, the considering the components of force and momentum in the x direction only. So, consider the components of force and momentum in the x direction only. Then what we could write, control surface rho u x u dot den is summation of f x, okay, and summation of f x would be T plus A E P A minus P E, which is net pressure force on control surface, okay. So, let say m dot A is rho u A I, which is here drawn into the engine per unit time. Then m dot E is rho e u e A e, which is the mass flow rate or mass flow rate crossing the exhaust areas, that is A e per unit time. M dot F is the fuel mass flow rate, which is mass of fuel consumed per unit time, and what we can write is that m dot E. So, now we can write the continuity equation, or or rather the total mass conservation. So, m dot exit, if you look at the diagram, this is where the mass drawn into the system, fuel is added, and this is where m dot E should be m dot A plus m dot F, which one can write that m dot F is rho E u E A E minus rho u A I. So, this is a very important information, that you get the total mass balance. So, the mass which comes in, that is the air comes in. So, typically the subscript that we use, this will follow whether it is air or fuel or exhaust, so that it makes it bit easy or consistent to understand the things. So, this is what you get in the mass balance. We will stop it here and find out the thrust and all this expression in the next discussion.